Okay, guys, so this video is about energy, damping, and resonance. Okay, so in particular, we're just looking at what's happening to the simple harmonic motion energy. So, well, let's say if we ignore friction and there's no driving force on the outside, it's just simply a pendulum bouncing, and it's just gonna keep bouncing. There's no friction. Okay, let's see what happens. What happens is the total amount of energy will always equal to the kinetic energy and the potential energy. Okay, so when it's at equilibrium, so a lot of potential energy, and it becomes fast kinetic energy, and then turn back to potential energy, kinetic energy, potential energy, kinetic energy, potential energy. So it's just gonna bounce like that. And same for bouncing spring situation. If we're bouncing up and down, at the top, lots of potential energy. It could be gravitational potential energy. It could be the springs elastic potential energy as well, and then it's going to push, become kinetic energy. Say this is equilibrium, slow down and speed up, slow down, speed up, slow down, speed up, slow down, right? So these energy is going to be changing. Okay, all right. In our notes, I write on the bottom of time. I mean, time will change as well. But the most common graph they actually ask you to draw is going to be this one. Okay, as I say, this has been a really old notes. So let's have a look over here. So the total amount of energy will need to stay the same. The reason why is because if there's no friction, there's not going to be any energy loss, and we have conservation of energy. Okay, all right. Total amount of energy stays the same, and energy also cannot be a negative value, so it will never be at the bottom over here. So the graph will be like here. So at the end position, that's when the potential energy is going to be the biggest. Okay, so we're starting with potential energy is biggest. And then potential energy is going to decrease and turn into zero when it's at equilibrium. Equilibrium is where kinetic energy is the biggest. So if I want to draw kinetic energy at the end is going to start from here, right? And then at equilibrium, it's going to reaching the maximum value. And then kinetic energy will be minimum at the other end. But these two always add together. The red one and and this one, they will always add up to become the total amount of energy. Okay, so that is that graph. Okay, so another graph is going to be this one. Is okay, what happens if we consider friction? If there's any friction, and friction will be able to take away some of the energy, so the energy will be gradually reducing. Okay, so now this graph, if I draw a time graph, let's say this is going to be my displacement. Okay, so I'm going to draw some dots to show the time. A bit longer. Okay, so let's say displacement, we started from the maximum position. So normally is we put it to the maximum position and we let go. Okay, okay. So say here, say the period is gonna be 0.4 second. That will be 0.5, 0.6, 0.7, 0.8. Okay, so that's two periods, 0.3, 0.2, 0.1. Okay, so when it falls down, say it's going to go to 0.1. Okay, and then through this whole process, some energy will be lost. So when it's reaching the bottom, it's not going to be as much as over here. Okay, say this starting with say 0.5, and when it comes down, maybe we'll only be able to reach 0.4. So it's not going to be that much anymore. Okay, all right. The students here commonly they make a mistake is this. So when they come here, they say, okay, it's going to be 0.4, like that. And then they're going to go, okay, it's going to reduce a bit more, Okay, see what's wrong with this? So for 0.1, it has landed from 0.5 to here. It only went a quarter of a period, right? So from here, it's to equilibrium. And it haven't gone here and here. But for over here, it has gone to the bottom and come back. So that is a half of a period. So that's a very common mistake. So I want to point it out over here, okay? So be careful when you draw this one. Okay, so now let's redraw it. 0.1, 0.2, 0.3, 0.4, and these are seconds. Okay, so say here. Now, from over here, it's gonna reach, say, maybe 0.45 or something. So it's gonna be a little bit smaller than that one. So it's gonna reach over here, and then come down to here, and then it's gonna reduce again, smaller than this one. And then smaller again. Okay, and then smaller again. So the amplitude is smaller because the energy becomes smaller, okay? So, and then it's gonna keep going, okay? And one other thing is this decrease is gonna be an exponential decrease. So I should draw this one a little bit higher. So an exponential decrease means the energy loss over here. Use a blue pen. The energy loss over here, over this period, from here to here, will be more than the energy loss during this two periods, this time. Okay, and the reason for that is when you are over here, the speed is really fast. This period speed is faster, so there's more friction. So this period will lose more energy, and I come to here and lose less energy. So what happens is the first swing always lose the most energy, and then lose a bit less. There's less energy in there, but the loss is going to be at a slower rate. Okay, so that's why this is going to be an exponential curve. Okay, all right, and then so that's damping. Well, what if we want to stop damping? For example, a typical example of damping is, say, if we close the door, right? Some door is sliding, and then boom, 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 they just go like that, and they stop, right? And another situation of damping is, say, our car goes around a bump, and then it might just bounce up and down a little bit. But sometimes we want to reduce it. Sometimes we want it to not damp so much sometimes we just want it to release to the zero. Say we close the door, we put a lot of friction there, so then it wouldn't cause simple harmonic motion. It's just gonna go straight into there. So then the door wouldn't go one. So it just closes. Okay, so stop the simple harmonic motion with damping, lots of resistance. Okay, so then another situation is where we might have what we call resonance. Okay, what is resonance? Resonance is if we have a constant force going to be added into the thing, so everything have a natural frequency. Okay, so the typical example we use is a swing. So if a child is swing is coming, give it a push, coming, I give it a push. So now I have a driving force. And this driving force, if it can matches the natural frequency of the swing, and then the energy can consistently be adding to the system. If energy is consistently added into the system, and then there will have lots of energy. If there's lots of energy, then the amplitude becomes really big. Okay, so amplitude becomes really big. So in this way, I can draw a graph. So this is my driving frequency. And this is going to be the amplitude. Okay. If my frequency don't match the natural frequency, say this, if the girl is coming, and before she reaches the end, boom, I give it a push. Well, that actually will stop the girl from coming here. The energy did not add it into the system. Rather, you're trying to stop it from coming at you and slow it down, right? So then it will not create a big amplitude, and there will be no energy added into the system. So I have to match the frequency of her. I can't just go boom, 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 super fast, right? If I go slow, and then that does not match her natural frequency, resonance cannot happen as well. So what happens is here, so the girl will have a natural frequency, let's call it F0, okay? So that is a natural frequency, and I'm gonna change my frequency So when the frequency is small, they're not in sync with the natural frequency, the amplitude will be small. There's not much energy added into it. But when the frequencies start to get close to this F0 value, natural frequency value, and then all of a sudden your amplitude becomes really big. And then becomes small again. Okay, so this is what we call resonance. So resonance happens when the driving frequency equal to the natural frequency. Yeah, so in the book, I talked about there is this video called Tacoma Bridge. So you can go research about it on YouTube. So you'll see a video of it. The natural frequency of the wing the driving frequency of the wing matches the natural frequency of the bridge. So that caused the bridge to start like big vibration. Okay, eventually the bridge fell because of resonance. And also another video of it is about if there's an earthquake. So if there's an earthquake, so the building, when we design it, we have to make sure like the building's natural frequency will be different from the frequency of the earthquake. Because when the earthquake's shaking, it gives you a frequency. If your frequency happens to match the earthquake frequency, then your building will just gonna go swing like crazy because energy is gonna consistently add into the system, cause a big amplitude, right? But if we got, so we can somehow design the building, what we can do is we can add a damper. So I'll show you a video of a damper as well. So you add a damper into there. So what happens with the damper is this, is when the building is swinging that way, the damper is swing this way, okay, and bring the building back. And then when the building swings this way, the damper goes that way. So it just goes like opposite to where the building is gonna be moving. So in this way, then they can kind of like stop the building from like all swing this way and energy getting this way and getting this way, and then for the building to break, okay? So yeah, about Tacoma Bridge is like, I think after Tacoma Bridge, when they design other things, they start to be more aware of that. So I think the next one about after Tacoma Bridge was a Golden Gate building, if I didn't remember it wrong. And then what they did with the design was very, very hollow in the middle, and then it changes the natural frequency of the bridge for some reason. Okay, all right, so and there's another simulation on fit as well. What you can do is you can change the frequency, so you can have a lot of springs. So it looks like this shape, and then you can add a lot of springs with the mass on it. So each of them will have a different natural frequency, and then there's a little turning thing. You can change the frequency, and then you still see which one is gonna matches your natural frequency, and then cause a big vibration. Okay. All right. So now I'm gonna also explain one question using the booklet over here. Okay, so spring of force constant of this. Okay, so we know spring constant, which is K, equal to 20 Newton per meter, has a load mass of 2.0 kg attached to it, and the load is pulled, so it extends the spring by 10 centimeter. Okay, so the extension, now I'm gonna write amplitude because the extension is gonna be the amplitude. The amplitude is gonna be 0.01 meter released. Okay, first we calculate the total oscillation energy of the load. Okay, so this one they already give you the equation. Okay, this is also the maximum amount of elastic potential energy. So this is basically the equation of elastic potential energy, and when we give it that 0.01, the amplitude, that's how much elastic potential energy you started with, and that is the amount of total energy it's going to turn into kinetic energy. Okay. All right, so that equals to half times 20 times 0.01 squared. Okay, so put in the calculator, so it should give me, so that is 10, 0.001 joule. Okay, that's a very small value. Okay. Oh yeah, it's a very small value because the spring constant is very small. Think about it. For 1 meter, you only put 20 Newton on it. 20 Newton is basically 2 kg of object, right? You put a 2 kg object, you extend it like 1 meter. So that's a very, very small spring constant. Okay. All right. B. What is the kinetic energy of the load as it passes through the center position? Okay. If we are ignoring friction, then we definitely be ignoring friction. Otherwise, we can't answer this question. Okay. If we're ignoring the friction, the EK max will just equal to the EP max, which equal to the E total, okay, total energy over here. So that's 0.001 joule. Okay, so if I draw it, you started with 0.001 joule of elastic potential energy, and then bam, EP equal to this, and then that's EK when equal to 0. Okay, when EK equals to max over here, that's when the EP becomes 0. Okay, so all right, so the next one, see what is the total oscillation energy of the system when the load is 1 centimeter from the central position. Okay, so total energy of the system. Well, the total energy just do not change. The total energy still equals to 0.001 joule because that total energy do not change. Okay, so the question could be a little bit more difficult. It might ask you, well, how much is the potential energy you have over here? If you ask you how much potential, well, that total energy could be made of potential energy and it could be made of kinetic energy. So they might ask you to calculate each of them. So we can have a look. What do we do if we calculate each of them? So then potential energy over here, EP is going to equal to half kx squared. Okay, and then what is k? K is still 20, and then x now is 0. Oh yeah, that's 0.1 meter. I did that wrong. That's why it's not that small. Okay, then it's 0.1 joule. Okay, my bad. Okay, and then over here, I'll change that as well. Okay, and then over here we go, well, x, so now that is 1 centimeter. 1 centimeter is 0.01 squared. Okay, so that equals to 0.001. That's what we had before. Okay, joule. Okay, if this is going to be 0.001 joule, and then how much kinetic energy do we have at this time? So EP is going to equal to the total energy, which is 0.1 joule, minus the 0.001 joule. So that gives me 0.099 joule. Okay, so yeah, if it's a little bit more difficult question, it will be over here. Okay, so for question 2, 3, and 4, you guys can have a try. Question 4 seems like to be a difficult question. So Mrs. John has written the answer, which I've uploaded onto Google Classroom. You can have a look if there is any question about it. So let me know and I can explain it to you. Okay. All right. So this is basically like the last lesson for this topic over here. So now I'm gonna give you guys a little bit of time to finish the questions over here and then the assignment. Okay. All right. So what I need you guys to do is to hand in the to take a picture of your assignment and upload it onto the Google Classroom so that I've seen you've completed the assignment, and then we'll move on to the next topic. And I want to make sure that everyone finish it, and then we can move on. Okay. So we are a little bit ahead of schedule compared to other classes, but obviously that's going to be an advantage for you guys. So make sure that you get that done, and then we're gonna move on to the next topic. All right, have a good day and stay safe, and just keep me posted how you're getting on, and send me an email if you have any questions. Okay, bye.